I see the time? Okay, well, I'll put it here. Thank you. Thank you.
Everybody?
So I need to finish at
12:25.
12:25.
So, our first speaker,
Thanks.
Alina Cojocaru, is going to give the first lecture on something with Frobenius.
Okay, am I on? Okay, hello everybody. I'm Alina Cojocaru. I'm Romanian, so that's a Romanian name. And I work at the University of Illinois at Chicago. And it's a great privilege for me to be here. So I want to thank the organizers for inviting me here. It's also a great joy. I came here for the first time in 2001 as a graduate student. And then again in 2002 as a graduate student, and my participation in this school had a great impact on my future activities as a math researcher. Okay, am I too quiet? Or not quiet, but too soft? Okay. Okay. No, did I do it right? Okay. 1, 2. Okay, so if I'm going to write Romanian cursive, which I just learned is not the standard cursive, but I don't want to change my cursive today. So anyhow, if you don't understand one of my letters, let me know. And if I write too small, let me know. And if anything you want to communicate, let me know, okay? Okay. All right, so what I want to talk about today is, all kinds of investigations along the theme of distributions of Frobenius in GL extensions. And, well, I know GL is not, I should have been more specific. So I'm going to talk a lot about GL2 extensions. And I want to start in a more elementary way and, how should I say, specify that I'm going to talk about about distribution of primes, so questions about primes in arithmetic geometric context, and in particular in the context of elliptic curves. So let's see how I'm going to write this theme. Distribution of Frobenius in GL extensions, which means I'll talk about questions about primes in arithmetic geometry, and more specifically, I'll focus first on elliptic curves over Q. Okay, and the guiding questions will be to look at the analogies between the groups Fp star and the group of points of an elliptic curve E defined over a finite field Fp. Okay, so what will be the main properties of Fp star? Well, this is a cyclic group, isomorphic to Z modulo P minus 1Z. So this is cyclic of order equal to exponent, which is P minus 1. And what we want is to look on this side and see if we have any similar properties to E of Fp. So our guiding questions will be question 1. Given an elliptic curve E over Q, how often is the group E bar of Fp, the reduction of E modulo P, cyclic? And the second question that will guide our lectures will be in the same setting, given an elliptic curve E over Q, how often is the order of the reduction of E mod P for a prime P that varies close to the exponent of this group. Okay. Okay, so let's see. I'll move here. So first, let me say a few words about primes. And then I'll say a few words about elliptic curves. And I don't think today I'll have time to explore these questions, but remember these are our guiding questions. Okay, so I was debating whether to tell you the definition of a prime. Of course, I know everybody knows the definition of a prime, but I do have the definition of an elliptic curve. So for symmetry, I wanted to put this down too. So instead, I'm going to let you think about the definition of a prime for 1 minute while I'm going to write something here. Okay, so the basic question is how many primes are there? And of course, we know the answers. And from the answer, let's say, finding the answer to these questions spans more than 2,000 years. So I'm going to just summarize here the history, starting with Euclid and ending with Adamar and de la Vallée-Poussin. Okay. I guess you don't understand what I wrote. That's Adamar. Okay, so let's see. From Euclid, we know that there are infinitely primes, and let's check who knows the lower bound for the counting function primes p up to x that comes from the proof of Euclid. Pi of x, yes? Say loud. No? Okay. Yeah. Okay, log x. So very far from anything, like x over anything. Okay, then after Euclid, we have work of Euler on pi of x. And let's see who knows this. So we gain a bit from the work of Euler on prime numbers. We know that the prime counting function grows at least like a constant times natural log of x. Then what the truth should be was predicted by Gauss and Legendre. So, okay, I hope everybody knows this. What should the truth be? X by log x. So this at this point in time was a conjecture. Okay, and then we have the work of Chebyshev. Okay, so let's see. I'm spelling Chebyshev in this particular way. So let's put some years here. Late 1800, and here's 1850s. So Chebyshev proved almost the prime number theorem, but not really. So he proved upper bounds and lower bounds in terms of x by log x times constants that are very close to 1, but not 1. And everything here was done through elementary methods. So then comes Riemann, who discusses the connection between the Riemann zeta function and pi of x. And finally, we have de la Vallée-Poussin and Adamar, who proved the prime number theorem in 1896. So pi of x is indeed asymptotically equal to x by log x. Okay, so this was a reminder of what we know about primes. And the next reminders will be some of the things that we know about primes in patterns, or patterns in primes. All right, so all of you must know that using Euclid's proof that there are infinitely primes, we can prove that there are infinitely primes in certain arithmetic progressions. Now, if you want to generalize Euclid's proof to prove that there are infinitely many primes in any arithmetic progression, you will reach a big obstacle. You cannot do that in general. However, using L functions, you can do that in general, and that was a result mentioned a few times today. It's Dirichlet's theorem for primes in arithmetic progressions, which states that if we have any a and m integers with m greater than or equal to 1, and GCD of m and m1, the function pi of x a, which counts primes p up to x, p will always denote a prime here, p congruent to a mod m, satisfies the asymptotic 1 over Euler function of m times, what did I write here, pi of x. And this is in the version following the work of de Lavalette, Poussin, and Adamar. Okay, and it was also mentioned that this is a particular case of the Chebotarev density theorem when we specialize the Chebotarev setting to that of a cyclotomic fields, Q of zeta m. So let's recall this one for any K over Q, I should have called capital M, finite Galois extension, and any C conjugacy class in the Galois group. So this is just one particular case of Chebotarev. The function pi sub C of x and K over Q, counting primes P up to x, and ramified in the extension such that the Frobenius at P equals this C satisfies the asymptotic. This is asymptotically equal to the size of C divided by the size of the extension times pi of x. Okay, so these are two classical results about primes, infinitely many primes in various patterns. And there are other conjectures which have some answers and have to do with primes that describe primitive roots. So we have Artin's primitive root conjecture, which is a theorem on the GRH. And we have conjectures by Hardy and Littlewood and many others. So let me state this one for any alpha integer different from 0 and -1 and a square. We expect to find a constant that's positive such that the number of primes p up to x, for which the group fp star is generated by alpha mod p, is asymptotically equal to the constant times pi of x. And I chose this one, so this is a conjecture here, but it's a theorem on the GRH.
For any particular alpha?
So what's known unconditionally is given any three numbers which are, let's say, chosen independently in some sense, at least one of them satisfies Artin's primitive root conjecture, but you don't know which one. That's the best that's known unconditionally.
We don't have any example, right? We don't have any particular alpha.
No theorem that says this particular alpha satisfies Artin's primitive root conjecture, but any alpha with any other two, you know that from in that set you'll find at least one, but you don't know which one. Yeah, but under GRH you know that this is true. Okay, so I chose this one here first of all because in the direction of elliptic curves we'll take this in that setting, and second of all because when we study Artin's primitive root conjecture, you have to understand better versions of Dirichlet and Chebotarev that I stated here. And I wanted to state this because I want to state them right now in the versions that we actually need. Okay, let's see how I do this here. So what I should have labeled this one. So what Artin's conjecture, or work on Artin's conjecture, leads to is understanding pi of x a for varying moduli a and for large moduli a. And similarly, you may want to think understanding of pi sub cxkq for lots of k, or varying k, infinitely many. And this brings us to using sieve methods and the theory of L functions to better understand Dirichlet and Chebotarev. So you'll have precise statements in your notes. So I thought that I'll just put them here at the level of maybe names. So in the direction of primes in arithmetic progressions, we have the Ziegel-Wolfish theorem that tells us the error term in that asymptotic formula Okay, so this is what I wrote in my notes. Did anybody write this in their lectures today? Because nobody wrote error terms, yeah? But you have them in my notes, so I'll not write them all down. But let me write this one. Is, well, roughly of size x divided by a huge power of log x. So I'll write it as x times exponential of minus a constant times square root of log x, where this is true for any a greater than 0 and any modulus m less than log x to this power. And c is a constant that depends on our a. So we have an effective version of Dirichlet's theorem, provided that the modulus m doesn't grow too fast as x grows. And if we want this modulus to go faster, we have to assume the Riemann hypothesis for Dirichlet L functions. So I'll call this effective Dirichlet, which says that, how did I state this? For any m less than x to a half divided by a log power, and for any a co-prime to m, we have another effective version with a better error term here. Provided the Riemann hypothesis is true. So let me emphasize the error term, x to a half instead of x times the log factor. And this is if and only if RH for Dirichlet functions, let's say GRH, is true. And we have similar versions for Chebotarev that were obtained by Lagarias and Odlesko. And they are stated in my notes. Okay. Now, if we want the modulus m to be larger than what we have here, let's see, larger than x to a half divided by, yeah? Sieve methods and L functions to better understand Dirichlet and Chebotarev. Okay. So if we want to understand primes and progressions for even larger moduli, we have many results, and I'll just recall at the level of labels right now, the very standard ones. We have the Brun-Titchmarsh theorem, which gives us an upper bound, but for very large, maybe I should recall it, for any m, okay, for any epsilon greater than 0, for any m less than x to 1 minus epsilon, and for any a, pi x m a is bounded from above by a constant times x divided by 5m log x over m. So we were able to increase the modulus, the length of the modulus here, but what we lost is the asymptotic. We only have the upper bound. If we still want to keep the upper bound, if you want to keep the asymptotic, but and you want to enlarge the modulus, you cannot do as well as Brun-Titchmarsh, but you can do things on average. So we have something called the Barban-Davenport-Halberstam. So who is familiar with these statements? Okay. Okay, I thought that not too many people were familiar, so that's, but they are really standard in analytic number theory. And then we have Bombier-Vinogradov. So let me state Bombier-Vinogradov, which says that for any a greater than 0, there exists a b greater than 0, such that when we look at the error term in Dirichlet's theorem, so this is an absolute value here, and then we average. So we take the maximum over the residue class A, and we take, oh, okay, there should be a y here. We take the maximum of a y, and then we average over m, and the good news is that we average it in a range that's better than what, a range similar to the one provided by effective Chebotarev under GRH. We get what GRH gives us, but without any GRH. Okay, so all these are standard in analytic number theory, and there are better results right now than what we have here, and they can be proven using sieve methods. On the side of Chebotarev, there are some results, so there is some variant of Brun-Titchmarsh due to Lagarias, Montgomery, and Odlyzko. These are already old results. But on the side of Barban-Davenport, for the analog of Barban-Davenport, Halberstam, and Bombier-Vinogradov, there is not much here. So what we'll do in these lectures, we'll look at variations of this averaging over primes in progressions in Chebotarev context, where we pick the fields K as division fields of elliptic curves. Okay, so this brings us to learning some things about elliptic curves. Well, so I thought I will give you the definition, but so let's say an elliptic curve E over K, even though Drew did not want to start with the definition. An elliptic curve E over field K is a smooth projective curve of genus 1 with a fixed point that we call O, and we view as a K rational point on the elliptic curve. And when K is equal to Q, which will be our focus, we'll describe them by Weierstrass equations of the form y squared equal to xq plus x plus b, where we can choose a, b to be integers. We need to choose them so that the curve is smooth. So delta E, which is delta AB, minus 16 times 4aq plus 27b squared, should be non-zero, and the point at infinity, given in projective coordinates by 0, 1, 0, is viewed as a point on this curve. So I assume many of you are familiar with this, but I also put lots of stuff in the notes about elliptic curves. So for the proofs, I refer to Silverman, Tate, Washington, and whatever other book you want. But let's just recall a few things about elliptic curves over Q. So let's recall Mordel's theorem. which tells us that E of Q is a finitely generated abelian group. So it's of the form Z to some integer greater than or equal to 0 times the group of points of finite order. Then May's theorem, which classifies the torsion. Was this in anybody's lectures? I don't think it was. Oh, okay. So this was one of my exercises. Many of these things, I wrote a set of exercises for these lecture notes. So one of the exercises is to prove Mordell's theorem. Another one is not to prove May's theorem, but to prove the to prove the version of May's theorem for CM elliptic curves, which is not that difficult. Then you can also use May's theorem to prove that. So if you want to, if you are in my study group, that's what you have to do, to give some proofs. You outline the proofs of some of these statements. Okay, in terms of the rank, we, as you know, this is part of a big open question, finding the rank in general, the Birch and Swinnerton-Dyer conjecture, which I'll only state like this. R is supposed to be given as the order at s equals to 1 of the L function of E S. Okay. Well, now when you investigate, say, the proof, not the proof of May's theorem, but ways of finding the torsion, understanding the points of torsion, a finite order on E, or understanding the rank, what you have to do is to reduce your curve modulo primes P. And if you have information about sufficiently many, but finitely many primes P, then you can find the torsion. Now, to understand the rank, you have to have information about these reductions for infinitely many primes P, or all but finitely many. So we can summarize that as a comment, but to really understand it, you have to do a lot of work. So the comment will be that to understand E over Q, say E of Q torsion, and R, we need to understand E mod P for finitely many primes P, and for infinitely many primes P, respectively. And in particular, what we need, so in particular, to understand the torsion, what we need is to understand the group structures of E mod P, which I'll denote by E bar of FP. So what's this as a group? And for the rank, we want to understand what the size of this is. Or we want to understand the TP, which I'll call AP, the TP that was introduced by Drew, and which I'll call AP, standardly order. Okay, so this brings us to two new questions. Given an elliptic curve E over Q, what is the group structure of its reduction, mod P, as the prime P varies? First for fixed prime P, then as the prime P varies. And question 2 prime, given an elliptic curve E over Q, what is the order of this group for prime P that's fixed and as the prime P varies? So structure and order. Well, yes? Down. Okay. So, towards answering these questions, we should talk about division fields of elliptic curves. So the setting will be that of an elliptic curve over Q. And M will be an integer. So then we define E of M, the group of M division points on the elliptic curve, which we know is isomorphic to 2 copies of Z modulo MZ. And we also know that the absolute Galois group of Q acts on this. So we get a family of representations. So I'm going to use the notation phi E sub M, defined on the absolute Galois group of Q, G sub Q, or gal of Q bar over Q, into GL2 of Z modulo MZ. And then moving vertically, we get phi of E M infinity, which will be a representation on GQ to GL2 of Z sub M. And then moving vertically, we get phi sub E, which is a representation on GQ into GL2 of Z hat. So here, Z hat, let's say, is the product of the alladics over all L, and Zm is the product of the alladics, the L where L divides M. All right, so now there are a few questions. What do we know about these representations, and why do we care about these representations? Well, so we care about these representations for many reasons. I want to relate information about them to information about the groups E of Fp and as the prime, for prime P that's fixed and as the prime P varies. Okay, so let me say a few words about this. Some properties of these representations. First of all, they depend on the structure of the endomorphism ring of E over Q bar, which is either Z, in which case we say that E is without Cm or non-Cm, or is isomorphic to an order in an imaginary quadratic field of class number 1. In which case we say that, so this is 1, is Cm. All right, so now, well, so we have two types of theorems depending on one case or the other. So theorem 1, let's be in the Cm case, order O. Let's call this order O. Okay, so assume that and Q bar of E is isomorphic to O. Define O hat as the inverse limit of O MO. And then also define K to be the field of fractions of O, which we said is an imaginary quadratic field of class number 1, and GK to be the absolute Galois group of K. Then the theorem says that, let's see. Okay, so when we look at this representation phi E and we restrict it to G sub K, we get the representation here that has image in GL1 of O hat, which is the unit in O hat, and this representation has open image in the sense that when we look in O hat star and the index of phi E of JK, in here this is finite. Okay, in particular, this is something that we'll use later on, we obtain that there exists an integer m, which we choose to be the smallest with the following property. So the smallest one I'll call m sub e, integer greater than or equal to 1, such that for any other m greater than or equal to 1 integer, the Galois group of k of E of m over k is isomorphic to the inverse image, so I'll call this omega and I'll say what it is, of k of E of the GCD of m and me over k, where this omega is the natural projection from O MO star to O of the over GCD of ME O star. Well, if you are not familiar with this, that's okay. Yeah? But if you're familiar, this is a standard in complex multiplication theory. So we'll come back to this. The bottom line is that we understand what these division fields are very well in the CM case when we move over the CM field of the elliptic curve, and that they are all abelian. Now in the non-CM case, what we have is something different. Another open image theorem. This one is due to Serre, which says, okay, so we assume that the endomorphism ring of E over Q is Z, then phi E has open image in GL2 Z hat, i.e., when we look at the index in GL2 of Z hat of phi E of JQ, that's finite. And in particular, we have an integer like ME before. In particular, there is an integer ME which is chosen as the smallest, such that, let's see how I wrote it here. Phi E of GQ is the inverse image of let's put phi E of ME of GQ, where omega is the natural projection from GL2 of Z hat into GL2 of Z modulo MEZ. Okay, so let me just check. Who has seen statements like this? Okay. Okay, so this is a safe territory. Okay. So let me summarize consequences of these results. Consequences, well, there are several consequences. One is that we understand these groups, the groups Q of EF square brackets of M, the Galois group of Q of EF square brackets of M over Q, we understand them reasonably well in the following sense. Well, in two senses, the structure but also the order. So in the sense of the structure, the order, we have the statement that if we have an elliptic curve E over Q, and if we define gamma to be 1 if we are in the generic case of non-CM curves, and 2 if we are in the case of a CM curve, then the degree of these fields generated by M division points is bounded from above by M to 4 over gamma, and from below by M to 4 over gamma times divided by log M. So in terms of the degree, we know what the degrees are. In terms of the structure of the Galois groups coming from these extensions, we know that for most M, in some sense that has to be clarified, and that is important to be clarified, the Galois groups of these extensions are GL2 of Z modulo MZ in the generic case, and they are far from that, but are well understood in the case of a CM curve, and well understood is in this sense. Okay, so now one of the next questions will be to look at the the maximality of the image phi of phi e. So it's a related question or emerging question. What can we say about the maximality of this group? Well, and let's clarify what do we mean by that. There is a lemma that was proven by Serre, which says that if we have an elliptic curve E over Q, then there exists a group that depends on the elliptic curve, subgroup of GL2 of Z hat, of index 2, such that this image, phi E of JQ, is always contained in HE. So the maximality of phi E of GQ means when is phi E of GQ equal to this index 2 subgroup HE. And in that case, we give a name to the curve, and that this is a terminology introduced by Lang and Trotta in the 70s. We call E over Q a Serre curve if we have equality here. And this means that when we look at how large the M division fields are for the given elliptic curve, they are as large as possible in this sense. The index of the Galois group of E of M, Q of E of M over Q in GL2 of Z modulo MZ is less than or equal to 2 for all, maybe I should emphasize this is for all M greater than or equal to 1. So what's remarkable to observe is that this index cannot be 1 for all M when you work with elliptic curves over Q. But that can happen when you work with elliptic curves over other number fields. So the most that you can hope for is to have less than or equal to 2 for all M. And, well, the question is, why would we look at this special case? So the answer, does anybody know the answer? Why would we look at Serre curves? I have a project on that too. The answer is that most curves are Serre curves. So if you care about generic elliptic curves over Q, one way of defining generic is not only by looking at non-CM elliptic curves, but non-CM elliptic curves that are Serre curves. Okay, so let me relate Serre curves with non-CM elliptic curves. We have this proposition. Let E over Q be a Serre curve. Then 1, it's a non-CM elliptic curve. 2, its torsion is trivial. So I'm going to leave this as an exercise to my groups. And 3, the ME that was introduced before this one can be calculated explicitly in terms of the square free part of the discriminant of any Weierstrass equation of the elliptic curve. So it's 2 times the absolute value of the square free part of delta E if this square free part is congruent to 1 mod 4, and it is 4 times the absolute value of the square free part of delta E otherwise. And then we have the theorem that says vaguely that almost all elliptic curves E over Q are Serre curves. So these are very good curves to work with. Well, and what you should ask is what almost all means. So almost all can mean different things, and there are various ways of counting here. So I'll state one later on, but I just want to mention that this comes in one way was done by Nathan Jones in his PhD thesis, then a a more geometric way of understanding this almost all Serre curves was done by Vinod Radhakrishnan in his PhD thesis. I guess it's 8. And then there are some work by myself with Nathan and David Grant that describes another way of interpreting almost all. So I'll focus on this one soon and draw from work of Nathan's PhD advisor Duke, who worked on this in the late 1990s, I believe. And here we'll see how analytic number theory can be used with arithmetic geometry to give results like this. Almost all? Okay, so you want the answer? Okay. Okay. Okay, so I'll give one answer. Okay, 13. Okay, so here is one, almost all. It's not all by finally many. That's not what it means. It means all but a zero density set. Almost all result. Okay, so let's see theorem. Let C of capital AB denote the set of Weierstrass or elliptic curves described by this Weierstrass equation. So elliptic curve over Q with little a in a box, little ab in a box. So we take Q isomorphism classes. Then let X be any real number greater than 0 tending to infinity, and you look at a x squared, capital B to be x cubed. Then let's see. One almost all result says 1 over the size of this family times the number of elliptic curves in the family, which are not Serre curves, is small as a function of x. It's bounded from above by x by log x to some c, which, so maybe I should say there. Okay, maybe there exists c greater than 0 such that for any this, so log x to this c divided by x. So this goes to 0 as x goes to infinity. And in this sense, the number of non-Serre curves divided by the in this family divided by the size of the whole family goes to 0 as goes to infinity. So that's one sense. Yes? It's hard to decide. Okay, so well, say it again and I'll repeat. It's hard to decide. So okay, I should repeat the question. Given an sure, okay, yeah. Given an elliptic curve E over Q, let's say, is there an algorithm to decide whether it's a Serre curve or not? And my answer is that it's hard to decide. You can decide whether it's CM or non-CM, but then to prove that it's Serre curve, it's hard. And well, I should say, so at the time of Lang and Trotta in the 1970s, there were 2 or 3 examples of Serre curves. And last year, there was a PhD thesis by Harris Daniels, who produced an explicit infinite family of Serre curves. So now we have infinite many to work with, but to decide in general when an elliptic curve E over Q is Serre curve or not is hard. Okay. So I'm going to, this result has been improved since then. So we have an asymptotic formula for this particular family. Moreover, using geometric methods. So now that you asked, let me write that. is equal to some constant times 1 over x squared plus, yes, thank you, plus a very small error term. But what I'll do in these lectures, well, if I have time, I'll just sketch the proof of a result, well, something weaker than what I said here, that uses a large sieve inequality, Ziegel-Wall-Fish, so primes in progressions for large, for small moduli, and well, then facts about, or the results about elliptic curves. Okay, how much more time do I have? 5 minutes? Okay, so then I'll now move on to talk about elliptic curves over finite fields. Let me just give you some ideas of how to use analytic number theory in arithmetic geometry by focusing on a weaker version of this result. So 14, sketch of an almost all result about elliptic curves. Okay, so let me state it. I have to say I'm not used to being in one place. I like to move around, you know. So, okay, I'm here. Okay, so we'll look at a weaker version of this theorem here, which is due to Duke. So Duke's theorem on torsion. And this result has also been improved using geometric methods, but let me sketch a proof using sieves. Well, so we consider the same setting. We consider the same family of elliptic curves defined by Weierstrass equations that we put in a box, and then we prove that there exists a constant c such that for any x greater than 0, 1 over the size of the family defined by x squared and x cubed times the number of elliptic curves in the family with non-trivial torsion. So remember, this is one of the conditions of having a Serre curve to having trivial torsion, but we need more than that for Serre curve. So this is weaker than this. Is bounded from above by log x to this constant c divided by x. Okay. So what are the ideas of proof here? So main steps in the proof. Okay, so let's see. Step 1. Well, we notice that if we have non-trivial torsion, then there is some prime L, so L and P in this course will be primes, such that the image of the model representation of the elliptic curve E is not the full thing that it can be. It can be GL2 of Z modulo LZ. And this means, so you should do the algebra here, there exists a determinant and trace not represented under this representation. So there exists a delta and tau in Z such that the function pi ex L delta tau counting primes P up to x such that P is congruent to delta mod L and AP is congruent to tau mod L is 0 for any x. On the other hand, if we have such an L, so this uses important work of Doering, let's say. On the other hand, if we're using important work of Massa and Wurstholz, we get that this L is bounded from above by log of the naive height of the elliptic curve to some constant. So if we have pick an elliptic curve E in this family, this would be bounded from above by log x to some other constant.
So could you repeat please the second implication? It's not clear.
Here, this,
Yeah.
this,
No. Yeah, this one.
this.
Suppose we have
Yes.
trivial L portions, so
So then L is bounded from above by the natural log of the naive height. This is maximum between A in absolute value and B in absolute value, defining the elliptic curve, raised to some explicit constant. And if you have E coming from this family, so your A and B are bounded by x squared and x cubed, that log of the height becomes log of x to some power. Is that what you wanted?
I mean, I just can't see a way you could.
Oh, I'm not proving this. This is hard. I'm just saying. Okay, no, this is really hard. So I'm invoking some results here. Yeah. This is Massa and Wuchtholz, and I would say this is some linear algebra plus Deuring. Let's say. Yeah, I'm not proving any of them. Okay. Yeah. Okay. Okay. So then the second step is to invoke a sieve using Gallagher's two-dimensional large sieve. We get that 1 over this, the size of this family times the sum over elliptic curves in the family of pi e x L delta tau minus some explicit constant depending on L, delta and tau, divided by GL2 of z modulo LZ times pi, so this is the number of primes being progressions. So this is coming back here, what we started with, has nothing to do with elliptic curves. This is bounded from above by x. So to wrap up, you put 1 and 2 together. 1, 2. You put results of Hecke and Deuring here on elliptic curves over finite fields. This is on Hurwitz class numbers plus Ziegler-Wolfish that I mentioned earlier, and you get this bound Duke's result. So this was one way of using, well, putting together lots of tools from arithmetic geometry, algebraic number theory, and classical analytic number theory to get something about the torsion of elliptic curves. Okay, so I'll answer questions about details of these proofs during the discussions on lecture notes. Yeah.
Yeah, maybe we'll save the questions for later, as Alina says, if that's okay. So yeah, we'll break for lunch, and we'll start again at 2:30. Thanks.
I can't, well, sure. I need to change this style. It's kind of, how do I turn this off?
Just 1 second, I should stop the recording.
Okay.